1. The setup, the test system by the numbers. To test their algorithm, the authors built a digital twin of a complex network consisting of exactly 3 interconnected nodes. Each node represents a dynamic subsystem like a drone or a power converter, and crucially, each node has a state described by 2 internal variables, for example, position and velocity. The network connections are not equal. The coupling matrix dictates that node 1 is influenced by node 2 at a strength of 0.25 and node 3 at 0.15. Node 2 is influenced by node 1 at 0.4 and node 3 at 0.15. Node 3 is influenced by node 1 at 0.1 and node 2 at 0.25. These specific numbers ensure the nodes are moderately chatty with each other, creating a realistic, messy interdependent system. 2. How coarse the quantization was. To save bandwidth, the system aggressively rounds the measurement signals before sending them. The quantization density, which determines how fine or coarse the digital steps are, was set to 0.87. This created a maximum rounding error of 6.95% per measurement. Furthermore, the sensor readings were assumed to have a maximum absolute amplitude of 12 units. Therefore, the worst-case rounding error introduced by the quantizer was strictly bounded by 0.83 units, which is 6.95% of 12. The algorithm had to guarantee that its tracking bubble was large enough to swallow this 0.83 unit uncertainty. 3. The heavy price of network congestion. Under the WTOD protocol, the system strictly enforced the rule that only one out of the 2 sensor components from each node could transmit at any given time step. This means 50% of the measurement data was intentionally thrown away at every single moment, replaced by stale, outdated readings. Over the course of the 150-step simulation, this aggressive scheduling forced the estimator to constantly compensate for missing data. For the ultimate test, accuracy, the RMSE numbers. The authors measured estimation accuracy using the root mean square error RMSE, a standard metric where lower numbers mean better tracking. They compared their proposed method against 3 alternative scenarios: ideal scenario, infinite bandwidth, with no quantization and no transmission delays. The system achieved an impressive average error of 0.4023. This is the theoretical gold standard. Quantization only, no scheduling, when they simply compress the signals but let everyone broadcast freely, the error barely worsened to 0.4089. This proves that rounding alone doesn't hurt much. WTOD protocol only, no compression, when they forced nodes to take turns without compressing the signals, the error jumped significantly to 0.5810. The stale, missing data caused a lot of confusion. The proposed method, quantization plus WTOD, combining both harsh realities, the algorithm achieved an average error of 0.6048. While this is slightly higher than the previous cases, the key takeaway is that the accuracy remained under 0.61 even under the harshest network constraints, and mathematically, the real states always stayed inside the calculated safe zone. 5. The Holy Grail, bandwidth savings. This is where the numbers get truly impressive. The authors tracked the total digital bits transmitted over the entire 150-step simulation. The ideal system, no restrictions, needed a massive 28,800 bits to send perfect, full-resolution data from all nodes. Using quantization only reduced that to 7,200 bits. Using WTOD only taking turns but sending full resolution used 14,400 bits. The proposed method, quantization plus WTOD, required only 3,600 bits. Translate that into percentages. Compared to the ideal system, the proposed method saved a whopping 87.5% of communication bandwidth. Compared to the quantization-only setup, it saved 50%. Compared to the WTOD-only setup, it saved 75%. In plain business terms, the algorithm achieved a good, workable accuracy and error of 0.6048 while using less than 1/8 of the bandwidth that the industry standard would require. 6. Stability, proving the bubble won't pop. A useless estimator is one that loses track of the target over time. The authors derived a strict numerical threshold to guarantee long-term stability. This threshold links the three nodes, the coupling strengths up to 0.4, the quantization error 6.95%, and the number of variables. When they plugged their specific numbers into this stability condition, the result comfortably passed the test. Consequently, the uncertainty bubble measured by the f-radius never spiraled out of control. In fact, the scale of the bubble peaked around a value of 80 during the initial transient phase, but within the first 80 time steps, it aggressively dropped down and stabilized permanently below 25 for the rest of the simulation. The algorithm found its footing and stayed tight forever. Summary of the numerical verdict. The paper proves with hard numbers that you can survive on a severe data diet. By accepting a tiny accuracy penalty moving from a perfect error of 0.40 to a constrained error of 0.60, the system slashes its bandwidth consumption from nearly 30,000 bits down to just 3,600 bits. For a factory manager or a drone swarm operator, that trade-off is pure gold. It means reliable, guaranteed tracking without needing to upgrade expensive network hardware.